Tonight, we're going to talk about something that sounds impossible. Albert Einstein, the man whose name has become synonymous with genius, the person who revolutionized our understanding of space, time, and reality itself, made a mistake. Not just any mistake, but what he himself called his biggest blunder. And here's what makes this story so fascinating. That mistake, that error in judgment that Einstein regretted for years, might actually turn out to be one of the most important insights in all of cosmology. It might be the key to understanding why the universe behaves the way it does. Before we dive in, if you find this exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. When you think of Albert Einstein, you probably picture wild white hair, a rumpled sweater, maybe a chalkboard covered in equations. You think of genius, of brilliance, of a mind that could see things no one else could see. And you'd be right. Einstein changed everything. He showed us that time isn't constant, that space can bend, that mass and energy are the same thing expressed in different ways. He gave us equations that predicted black holes, gravitational waves, and the expansion of the universe itself, decades before any of these things were actually observed. But Einstein was human, and humans make mistakes, even the brilliant ones, maybe especially the brilliant ones, because they're working at the edge of what's known, pushing into territory where no one has been before. There are no maps, no guides, no textbook answers. You're making educated guesses, following your intuition, hoping you're right but never entirely sure. In 1917, Einstein published a paper that added something to his equations. A single term, a constant he called lambda, the cosmological constant. He added it for one reason and one reason only: to keep the universe still, to prevent it from collapsing inward under its own gravity or expanding outward into the void. He wanted a static, unchanging universe, one that had always existed and would always exist. And to get that result, he needed to add this extra term to balance things out. 12 years later, in 1929, an astronomer named Edwin Hubble showed that the universe wasn't static at all. It was expanding. Galaxies were moving away from each other. The entire cosmos was growing larger with each passing moment. Einstein's cosmological constant wasn't necessary. The universe didn't need to be held still because it wasn't still. It was dynamic, changing, evolving. Einstein reportedly called this his biggest blunder. He'd let his philosophical preferences, his desire for a universe that was eternal and unchanging, cloud his scientific judgment. He'd added something to his equations, not because the math demanded it, not because observations required it, but because he wanted a specific result. And he'd been wrong. Except, and this is where the story gets really interesting, he might not have been wrong after all. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe wasn't slowing down as everyone expected. It was speeding up. Something was pushing the universe apart, accelerating its expansion. And the best explanation anyone could come up with was Einstein's cosmological constant, that term he'd added in 1917 and removed in embarrassment in 1929. It turned out to describe something real, something we now call dark energy. So Einstein's biggest mistake might actually be one of his greatest insights. A theoretical prediction made for the wrong reasons that turned out to describe a fundamental property of the universe. That's the story we're going to explore tonight. How Einstein came to make this mistake, why it seemed like a mistake for decades, and how modern cosmology has brought it back from the dead. Let's start at the beginning, with Einstein himself and the revolutionary ideas that changed physics forever. Albert Einstein was born in 1879 in the German city of Ulm. He wasn't a child prodigy in the traditional sense. He didn't speak until he was relatively late, and his parents worried about him. He wasn't the best student, often clashing with teachers who valued memorization over understanding. He questioned everything, pushed back against authority, and generally made himself difficult to teach in the rigid German school system of the time. His family moved to Munich when he was an infant, and this is where he grew up. His father Hermann was an engineer and businessman who ran an electrical equipment company with Einstein's uncle. His mother Pauline was educated and cultured, encouraging young Albert's interest in music. Einstein learned to play the violin and maintained his love of music throughout his life, often saying that he thought in music and saw his life in terms of harmony. The late 19th century was a time of rapid change in Germany and throughout Europe. The Industrial Revolution was transforming societies. Cities were growing. New technologies like electricity and telephones were becoming common. It was an age of optimism and progress, a belief that human knowledge was advancing rapidly and that science would solve humanity's problems. But Einstein had something more valuable than obedience or rote learning ability. He had an incredible imagination. He could visualize abstract concepts in ways that made them clear and understandable. He thought in pictures, in thought experiments, in scenarios he could play out in his mind. This ability to visualize the invisible would become his greatest strength. When Einstein was 5 years old, his father showed him a pocket compass. The boy was fascinated by the invisible force that made the needle always point north, no matter how you turned the compass. This was his first encounter with the idea that there were hidden forces in nature, things you couldn't see but could detect through their effects. That compass made a deep impression on him, planting a seed that would grow into his lifelong quest to understand the hidden workings of the universe. There's a famous story about Einstein as a teenager, imagining what it would be like to ride alongside a beam of light. If you could somehow match light's speed and travel next to it, what would you see? Would the light wave appear frozen, stationary, or would something stranger happen? This simple thought experiment, this act of imagination, planted seeds that would eventually grow into special relativity. He puzzled over this question for years. According to the physics of his time, according to Maxwell's equations of electromagnetism, which were the most successful physics theory of the late 19th century, light was a wave that traveled at a fixed speed through space. But if you could match that speed, if you could travel alongside the light, what would happen? The light wave should appear stationary from your perspective, frozen in time. But Maxwell's equations didn't allow for stationary light waves. Something didn't make sense. This paradox bothered Einstein throughout his teenage years and into his 20s. It suggested that either Maxwell's equations were wrong, which seemed unlikely given how successful they were at describing electricity, magnetism, and light, or there was something fundamentally wrong with how people thought about space, time, and motion. Einstein attended the Swiss Federal Polytechnic in Zurich, studying physics and mathematics. He was a good student, but not exceptional. He skipped classes that didn't interest him, preferring to study what he found fascinating rather than following the prescribed curriculum. This didn't endear him to his professors. When he graduated in 1900, none of his teachers would write him a recommendation for an academic position. This was a serious problem. In the academic world of the early 20th century, personal recommendations from your professors were essential for getting your career started. Einstein spent 2 years unemployed or underemployed, taking temporary teaching positions, tutoring students, doing whatever he could to make ends meet. It was a difficult, uncertain time. He'd invested years in his education, but the academic world seemed closed to him because he'd alienated his professors by not conforming to their expectations. After university, Einstein struggled to find an academic position. He ended up working at a patent office in Bern, Switzerland. It was a good job, steady and respectable, but it wasn't what he'd dreamed of. He spent his days evaluating patent applications, determining whether inventions were truly novel or just rehashes of existing ideas. It was steady work, but it left him time. Time to think, time to read, time to work on physics in the evenings and weekends. In 1905, Einstein's miracle year, he published 4 papers that changed physics forever. These weren't incremental improvements on existing theories. These were revolutionary ideas that overturned centuries of scientific understanding. The first paper explained the photoelectric effect, showing that light behaves as if it's made of particles, little packets of energy we now call photons. This work would eventually win him the Nobel Prize and help establish quantum mechanics, though Einstein himself would later have deep reservations about where quantum theory was heading. The second paper provided convincing evidence for the existence of atoms by explaining Brownian motion, the random, jittering movement of tiny particles suspended in fluid. At the time, not all scientists believed atoms were real, rather than just useful mathematical fictions. Einstein's paper helped settle that debate. The third paper introduced special relativity, showing that space and time are not separate, absolute things, but are intertwined into a single entity called spacetime. Time can pass at different rates for different observers depending on their relative motion. This wasn't philosophy or speculation. It was mathematics backed by experimental evidence. The fourth paper contained the most famous equation in physics. E equals mc squared. Energy equals mass times the speed of light squared. This simple equation showed that mass and energy are equivalent, that matter is essentially frozen energy. It predicted nuclear reactions, explained where the sun gets its power, and eventually led to both nuclear weapons and nuclear power. These 4 papers, any one of which would have been a career-defining achievement, were all published in a single year by a 26-year-old patent clerk working outside the academic system. It's one of the most remarkable achievements in the history of science. Special relativity was revolutionary, but it had limitations. It only worked for objects moving at constant speeds relative to each other. It didn't handle acceleration or gravity. Einstein knew this was incomplete. For the next decade, he worked on extending his theory to include gravity and acceleration. The result, published in 1915, was general relativity. General relativity is hard to understand mathematically. The equations are complex, involving advanced mathematics that most people, even most physicists, never study in detail. Einstein himself had to learn new mathematics, tensor calculus, and differential geometry, specifically to express his ideas. He worked with his friend Marcel Grossmann, a mathematician, to master these tools. It took him 8 years from the initial idea to the final, complete theory. 8 years of intense work, false starts, mistakes, and frustration. But the core idea is actually quite simple and can be understood without any math at all. Imagine space as a rubber sheet, stretched flat and smooth. Now place a heavy ball in the middle of the sheet. The ball makes a dent, a depression, in the rubber. The heavier the ball, the deeper the dent. Now roll a marble across the sheet. As it passes near the heavy ball, it curves toward it, following the contour of the depression. The marble isn't being pulled by some mysterious force. It's just following the natural shape of the curved sheet. That's how gravity works in general relativity. Massive objects like stars and planets don't pull on other objects with some invisible force reaching across space. Instead, they curve the space around them. Other objects move through that curved space, and their paths bend as a result. The Earth orbits the Sun, not because the Sun is pulling on it, but because the Sun curves space around it, and the Earth is following the straightest possible path through that curved space. Now, this analogy has limitations. The rubber sheet is two-dimensional and embedded in three-dimensional space. Real space-time is four-dimensional, 3 dimensions of space and 1 of time, and it's not embedded in anything. It's the fundamental arena in which everything exists. There's no higher dimensional space that space-time curves into. The curvature is intrinsic to space-time itself. Also, the analogy shows spatial curvature, but not temporal curvature. In general relativity, time itself is affected by gravity. Time passes more slowly near massive objects. This isn't just clocks running slow. It's actual time, the fundamental flow of causality. Two identical clocks, one near a massive object and one far away, will tick at different rates. The one near the massive object runs slower, and this has been measured with atomic clocks with extraordinary precision. Think about that for a moment. It's a completely different way of understanding gravity compared to what Isaac Newton proposed. Newton said gravity is a force, something that reaches out across empty space and pulls objects toward each other. Einstein said there's no force at all. There's just curved space, and objects move through that space following the natural contours of the curves. This might sound like just a different way of describing the same thing, but it's not. General relativity makes predictions that are different from Newton's theory. And every time we've tested those predictions, Einstein has been right and Newton has been wrong, or at least incomplete. Newton's theory says that if you suddenly removed the sun, the Earth would immediately fly off in a straight line. The gravitational force would disappear instantly and the Earth would no longer orbit. Einstein's theory says something different. If the sun disappeared, a gravitational wave, a ripple in space-time, would propagate outward at the speed of light. The Earth wouldn't feel any change until that wave reached it 8 minutes and 20 seconds later. Information about the sun's disappearance would travel at light speed through space-time, not instantaneously. General relativity predicted that light should bend when it passes near massive objects. In 1919, during a solar eclipse, astronomers measured the positions of stars visible near the sun's edge. The stars appeared slightly displaced from their usual positions because the sun's mass curved the space around it, bending the light from those distant stars as it passed nearby. This observation made Einstein world famous overnight. The newspapers ran headlines about how space was curved and reality was different from what everyone had assumed. This wasn't just abstract physics. Light bending around massive objects, called gravitational lensing, has become one of astronomy's most powerful tools. When a massive galaxy or galaxy cluster sits between Earth and a more distant galaxy, the foreground object's gravity bends the light from the background galaxy, often creating multiple distorted images arranged in rings or arcs around the lens. Astronomers use these natural magnifying glasses to study galaxies that would otherwise be too faint and distant to observe. Some of the deepest images of the early universe come from studying gravitationally lensed galaxies. General relativity predicted that time should pass more slowly in strong gravitational fields. This has been tested with atomic clocks, placed at different altitudes. A clock on a mountaintop runs slightly faster than an identical clock at sea level because it's farther from Earth's mass and therefore in a weaker gravitational field. The difference is tiny, only a few nanoseconds per day, but it's measurable and exactly matches Einstein's predictions. GPS satellites must account for this time dilation effect. The satellites orbit about 20,000 kilometers or 12,400 miles above Earth's surface, where gravity is weaker than at ground level. This causes their atomic clocks to run faster than clocks on the ground by about 45 microseconds per day. Additionally, because the satellites are moving at high speeds, special relativity causes their clocks to run slower by about 7 microseconds per day. The net effect is about 38 microseconds per day faster. This might sound insignificant, but GPS works by precisely timing radio signals. Light travels about 30 centimeters or 12 inches per nanosecond. If GPS didn't correct for relativistic time dilation, the errors would accumulate at a rate of about 10 kilometers or 6 miles per day. Within hours, GPS navigation would become useless. Every time you use GPS to navigate, you're relying on Einstein's relativity to be accurate. Your phone is doing relativistic calculations to correct for time dilation. General relativity predicted gravitational waves, ripples in spacetime itself, created when massive objects accelerate. These waves were finally detected directly in 2015, a full century after Einstein predicted them, when the LIGO experiment measured the incredibly tiny distortions in space caused by two black holes colliding over 1 billion light-years away. The measurement was so precise it could detect changes in distance smaller than a proton, and it matched Einstein's predictions perfectly. Since that first detection, LIGO and its partner observatory Virgo have detected dozens of gravitational wave events. Most involve colliding black holes, but they've also detected colliding neutron stars. In 2017, a neutron-star merger was detected both in gravitational waves and across the electromagnetic spectrum, from gamma rays to radio waves. This event confirmed theories about where heavy elements like gold and platinum come from. These elements are forged in neutron-star collisions and scattered across space to eventually become part of new star systems and planets. Gravitational wave astronomy is now an established field, giving us a completely new way to observe the universe. Unlike light, which can be absorbed or scattered, gravitational waves pass through everything unimpeded. They carry information about events that produce no light at all, like the collision of two black holes in empty space. As detectors become more sensitive, we'll observe gravitational waves from the early universe itself, potentially seeing events that occurred when the cosmos was too young and hot for light to travel freely. So general relativity works. It's been tested countless times in countless ways, and it always gives the right answer. It's one of the most successful scientific theories ever developed. But when Einstein first worked out his equations, he ran into a problem that would lead to what he later called his biggest blunder. The equations of general relativity describe how mass and energy curve space and time, but they're dynamic equations. They describe how things change, how space responds to the presence of matter and energy. When Einstein applied his equations to the universe as a whole, he found something troubling. The universe, according to his equations, couldn't remain still. It had to be either expanding or contracting. If you filled space with stars and galaxies, gravity would pull everything together, causing a cosmic collapse. Or, if things were already moving apart, they'd continue separating, the universe growing larger forever. But this contradicted Einstein's philosophical view of the cosmos. He envisioned an eternal, steady-state universe that had always existed and would always exist. This wasn't based on observations. It was an aesthetic judgment, a belief that the cosmos should be balanced and timeless. Most astronomers shared this view. In the early 20th century, they believed the universe consisted only of the Milky Way galaxy, a large but finite island of stars floating in infinite empty space. The fuzzy spiral nebulae visible through telescopes were thought to be gas clouds within our galaxy, not separate galaxies millions of light years away. If the cosmos was just our galaxy surrounded by void, then a steady-state model made intuitive sense. Individual stars were born and died, but the overall structure remained roughly constant. There was no reason to think the entire universe was evolving in any fundamental way. So, when Einstein's equations predicted an unstable universe that couldn't remain static, he faced a choice. He could accept what the math was telling him and conclude that the universe must be either expanding or contracting, or he could modify the equations to allow for a static solution. He chose the second option. In 1917, he published a paper adding a new term to his field equations. The cosmological constant, represented by the Greek letter lambda. This constant represented a kind of repulsive force, something that pushed space apart, counteracting the attractive force of gravity. By carefully tuning this constant to exactly the right value, Einstein could balance the inward pull of gravity with the outward push of lambda, creating a universe that was static and stable. The mathematics behind this was elegant in its own way. General relativity describes how the curvature of spacetime responds to the presence of mass and energy. The equations relate the geometry of spacetime on one side to the distribution of matter and energy on the other side. Einstein realized he could add an additional term to the geometry side, a term that represented a kind of intrinsic curvature of space that existed even in the absence of matter. This term, the cosmological constant, had interesting properties. Unlike normal matter or energy, which becomes more dilute as space expands, the cosmological constant stayed constant. It was the same everywhere, at all times. It represented a kind of energy density that was a property of space itself. The more space you had, the more of this energy you had, but the density never changed. If you doubled the volume of space, you doubled the total amount of this energy, keeping the density constant. It's important to understand what Einstein did here. He didn't discover the cosmological constant by observing something in nature or deriving it from more fundamental principles. He added it to make his equations give him the answer he wanted. The math allowed for such a term. There was nothing technically wrong with including it, but its only justification was that it produced a static universe, which Einstein believed on philosophical grounds must be correct. This wasn't the first time a physicist had modified equations to match desired results. In the history of science, there are many examples of ad hoc modifications that later proved necessary, and many more that proved to be wrong. The trick is that you can't know in advance which category your modification falls into. You have to wait for observations to tell you whether you were right or wrong. Einstein was aware of the somewhat arbitrary nature of this addition. In his paper, he noted that the cosmological constant was the simplest possible addition that would allow a static solution. He also noted that there was no independent theoretical reason to include it. Its justification was purely that it solved what he saw as a problem with his original equations, their prediction of an unstable universe. Think about what the cosmological constant actually means. It's energy inherent in empty space itself, even in a perfect vacuum, completely devoid of matter and radiation. This constant says there's a kind of pressure pushing outward. It's not particles, and it's not waves. It's a fundamental property of space. The more volume you have, the more of this energy exists. But crucially, the density stays uniform everywhere. In everyday life, forces weaken with distance. Gravity fades as you move away from massive objects. Light dims the farther you are from its source. But the cosmological constant behaves differently. Double the volume of space, and you double this repulsive energy while maintaining constant density. It's utterly alien to ordinary experience. Einstein knew this addition was unusual. He was introducing something fundamentally new to physics without direct evidence. But he did it anyway, because his equations demanded modification to achieve the steady-state cosmos he believed must exist. For the next 12 years, the cosmological constant sat in Einstein's equations. Other physicists debated whether it was necessary or justified. Some argued it was an elegant solution to a real problem. Others thought it was an ad hoc fix, something added to force a desired result, rather than emerging naturally from the theory. Then everything changed. In the early 1920s, an astronomer named Edwin Hubble began making observations that would revolutionize our understanding of the cosmos. Working with the 100-inch telescope at Mount Wilson Observatory in California, which was the largest telescope in the world at the time, Hubble studied the fuzzy spiral nebulae that astronomers had been observing for decades. These spiral nebulae were mysterious objects. Through small telescopes, they appeared as faint, fuzzy patches of light scattered across the sky. Through larger telescopes, you could see they had spiral structure, arms of light swirling around a bright central core. But nobody knew what they were. Some astronomers thought they were gas clouds within our own galaxy, perhaps regions where new stars were forming. Others speculated they might be distant star systems beyond the Milky Way. The debate about the nature of spiral nebulae was one of the great controversies in astronomy in the early 20th century. In 1920, there was even a formal debate on the subject between two prominent astronomers, Harlow Shapley, who argued the spiral nebulae were part of the Milky Way, and Heber Curtis, who argued they were separate galaxies. Neither side had definitive proof, so the debate ended without clear resolution. Hubble changed everything by finding a way to measure the distances to these nebulae. He did this using a type of star called a Cepheid variable. These stars pulsate, growing brighter and dimmer in a regular cycle that can last anywhere from days to months. The American astronomer Henrietta Leavitt had discovered something remarkable about Cepheid variables. Their period of pulsation, how long it takes them to go from bright to dim and back again, is directly related to their intrinsic brightness. A Cepheid that pulsates slowly is intrinsically brighter than one that pulsates quickly. This meant you could use Cepheids as standard candles to measure cosmic distances. If you could identify a Cepheid variable in a distant object, measure its period, you'd know how bright it actually was. By comparing its actual brightness to how bright it appeared from Earth, you could calculate how far away it must be. The dimmer it appeared, the farther away it was. Using a technique developed by Henrietta Leavitt to measure cosmic distances, Hubble determined that these nebulae were far outside the Milky Way. They weren't gas clouds in our galaxy. They were separate galaxies, each containing billions of stars, located millions of light years away. The universe was vastly larger than anyone had imagined. The first distance Hubble measured was to the Andromeda Galaxy, which appeared in the sky as a faint, fuzzy oval visible to the naked eye on dark nights. Hubble found Cepheid variables in Andromeda and measured their periods. His calculations showed that Andromeda was about 900,000 light-years away. This was later revised upward when we better understood Cepheid variables, and we now know Andromeda is actually about 2.5 million light-years away, but even Hubble's original estimate was far enough to prove that Andromeda was well outside the Milky Way. It was a separate galaxy, not part of our own. This was revolutionary. The universe wasn't just the Milky Way. It was filled with galaxies, countless islands of stars scattered through space, each containing billions of suns. The cosmos was far larger and more complex than anyone had imagined. What had appeared to be a universe, perhaps 100,000 light-years across, the size of our galaxy, was actually vastly bigger, filled with galaxies separated by millions of light-years. But Hubble didn't stop there. He also measured how these galaxies were moving. When you look at light from a distant object, you can determine whether it's moving towards you or away from you by examining its spectrum, the rainbow of colors created when you split the light through a prism. If the object is moving toward you, the spectrum shifts toward the blue end of the rainbow. If it's moving away, it shifts toward the red end. This is called redshift for objects moving away and blue shift for objects moving toward. Think of it like the Doppler effect with sound. When an ambulance drives toward you, its siren sounds higher pitched than normal because the sound waves are compressed. When it drives away, the siren sounds lower pitched because the waves are stretched out. Light does the same thing. Motion toward you compresses the waves, shifting them toward blue. Motion away stretches them out, shifting them toward red. Hubble found that nearly all galaxies showed redshift. They were moving away from us. And the farther away a galaxy was, the faster it was receding. A galaxy twice as far away was moving away twice as fast. 3 times the distance meant 3 times the speed. There was a clear mathematical relationship between distance and recession velocity. This could only mean one thing. The universe was expanding. Space itself was growing larger, carrying galaxies with it. The farther apart 2 galaxies were, the more space between them, and therefore the faster they appeared to separate as that space stretched. Think of dots drawn on a balloon's surface. As you inflate the balloon, the rubber stretches and the dots move apart. They're not sliding across the surface. The surface itself is expanding, carrying the dots along. That's what's happening with the universe. Space is the expanding medium, and galaxies ride along with it. In 1929, Hubble published his findings. The universe was not static. It was expanding, and had been expanding for a very long time. Einstein's cosmological constant, added specifically to prevent expansion or collapse, was unnecessary. The universe didn't need to be held still because it wasn't still. It was dynamic, changing, evolving. When Einstein learned of Hubble's discovery, he recognized immediately what it meant. He'd made an error. His philosophical preference for a steady-state cosmos had overridden what the mathematics of general relativity had been trying to tell him. His original equations, without the added constant, had predicted expansion all along. If he'd trusted the mathematics instead of forcing it to match his preconceptions, he would have anticipated the discovery before astronomers observed it. Instead, he'd modified his work to get the wrong answer. Einstein visited Mount Wilson Observatory in 1931 to see Hubble's work firsthand. He looked through the telescope, examined the data, and confirmed that yes, the universe was definitely expanding. According to the Russian physicist George Gamow, who was present during some of these discussions, Einstein expressed deep regret about adding the cosmological constant. He'd inserted it without good justification, except to achieve an answer he preferred philosophically, and that answer turned out to be incorrect. Einstein removed the cosmological constant from his equations. For the next few decades, it was largely forgotten, relegated to a footnote in the history of physics. A cautionary tale about how even great scientists can be led astray by their assumptions and preferences. But the story doesn't end there. The cosmological constant might have been added for the wrong reasons, but as we'll see, it turned out to describe something very real about the universe. Something that would remain hidden for nearly 70 years before observations finally revealed its presence. Let's talk about what an expanding universe actually means, because this is one of the most commonly misunderstood concepts in cosmology. When we say the universe is expanding, we don't mean galaxies are exploding outward from some central point into empty space. There is no center. There is no edge. Space itself is growing larger everywhere simultaneously. Remember that balloon analogy. Every point on the expanding surface moves away from every other point, yet no location is special. Each observer, wherever they are, sees the same phenomenon. All distant objects receding in every direction. The expansion is uniform throughout space. Now here's something that confuses people. If space is expanding, why aren't we expanding? Why isn't Earth getting bigger? The answer is that local forces completely overwhelm the expansion. Atoms are bound by electromagnetic forces. Planets are held together by gravity and chemical bonds. Even galaxies resist the expansion through their own gravitational pull. The expansion only dominates at the largest scales, the distances between galaxy clusters where no other forces can compete. The discovery that the universe was expanding immediately raised a profound question. If space is growing larger, that means it used to be smaller. Wind the clock backward far enough, and you reach a point where all of space was compressed into an infinitely small, infinitely dense point, a singularity. This was the moment of creation, the beginning of the universe itself. This idea was initially called the primeval atom by Georges Lemaitre, a Belgian priest and physicist who was one of the first to work out the implications of an expanding universe. Later, the astronomer Fred Hoyle would mockingly call it the Big Bang, a name that stuck even though Hoyle himself never accepted the theory. The Big Bang theory says the universe began in an unimaginably hot, dense state about 13.8 billion years ago. Space, time, matter, and energy all came into existence at that moment. There was no before, because time itself began with the Big Bang. Space expanded rapidly, cooling as it grew, allowing first subatomic particles, then atoms, then stars and galaxies to form. This raised immediate objections. Many scientists in the 1930s and 40s found the idea philosophically troubling. The universe having a beginning seemed to imply a creator, which made some scientists uncomfortable. It felt more like theology than physics. Hoyle and others proposed alternative theories where the universe was eternal, with new matter continuously being created to fill the gaps left by expansion. This steady-state model preserved the philosophical appeal of a timeless cosmos while still matching Hubble's observations of expansion. The steady-state theory had its appeal. It avoided the uncomfortable question of what came before the Big Bang. If the universe had always existed, there was no moment of creation to explain. New matter would appear gradually throughout space, spontaneously popping into existence to maintain constant density as expansion spread things out. The rate would be incredibly slow, about 1 hydrogen atom per cubic kilometer or cubic mile of space per year, far too slow to detect directly. For several decades, the steady-state model and the Big Bang model competed. Both could explain the observed expansion. Both made testable predictions. the scientific community was divided. Some found the steady state more philosophically satisfying. Others found the Big Bang more elegant mathematically. It was one of the great debates in 20th century cosmology. The debate wasn't settled by philosophical arguments, it was settled by observation. If the Big Bang happened, the early universe must have been hot and dense. As it expanded and cooled, there should be leftover radiation from that early hot phase, now cooled by expansion to just a few degrees above absolute zero. This cosmic microwave background radiation should fill all of space uniformly. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were testing a sensitive radio antenna at Bell Labs in New Jersey. They kept picking up mysterious noise, a faint hiss that came from all directions equally. At first, they thought it was interference, perhaps from nearby New York City or even from pigeon droppings on their antenna. They cleaned the antenna thoroughly, even removing nesting pigeons, but the noise persisted. Eventually, they learned that physicists at nearby Princeton University had predicted exactly this kind of background radiation as a consequence of the Big Bang. The noise Penzias and Wilson detected wasn't interference. It was the afterglow of the Big Bang itself, radiation that had been traveling through space for over 13 billion years, cooled by cosmic expansion from millions of degrees to just a few degrees above absolute zero. This discovery won Penzias and Wilson the Nobel Prize and essentially ended serious debate about whether the Big Bang had occurred. The steady-state model couldn't explain this background radiation. The Big Bang predicted it. So by the 1960s and 70s, the picture seemed clear. The universe began with the Big Bang 13.8 billion years ago. It's been expanding ever since. Gravity has been slowing that expansion, like a ball thrown upward, gradually slowing as Earth's gravity pulls on it. Eventually, one of two things would happen. Either there was enough matter in the universe that gravity would eventually stop the expansion and reverse it, causing the universe to collapse back in on itself in a big crunch, or there wasn't enough matter, and the universe would expand forever, gradually slowing, but never quite stopping. Astronomers work to measure the universe's total mass density to determine which scenario was correct. Would we get a big crunch or eternal expansion? The fate of the universe hung on this measurement. Einstein's cosmological constant was barely mentioned during these decades. It had been added to create a static universe. The universe wasn't static. Therefore, the constant was unnecessary. Just an embarrassing mistake. Case closed. But physics is never that simple. Just when you think you understand something, nature throws you a curveball. And in the 1990s, cosmology got one of the biggest curveballs in scientific history. To understand what happened, we need to talk about supernovae. When certain massive stars reach the end of their lives, they explode in spectacular fashion, briefly outshining entire galaxies. These explosions, called supernovae, are among the most energetic events in the universe. For a few weeks, a single dying star can emit as much light as billions of normal stars combined. The word supernova means new superstar in Latin. Ancient and medieval astronomers occasionally saw what appeared to be new stars suddenly appearing in the sky, shining brightly for a few weeks or months before fading away. They called these novae new stars, though we now know they're not new stars being born, but old stars dying in catastrophic explosions. A supernova releases more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. The explosion is so violent that it can briefly outshine an entire galaxy containing hundreds of billions of stars. The energy released is comparable to all the energy the sun will ever produce, compressed into a moment of unimaginable violence. When a star explodes as a supernova, it doesn't just release light and heat. It also forges heavy elements in its final moments. Elements heavier than iron, things like gold, silver, uranium, and platinum, can only be created in these extreme conditions, in the incredible temperatures and pressures of a supernova explosion. Every atom of gold in your jewelry, every atom of silver in your electronics, every atom of uranium in the Earth's crust was forged in a dying star billions of years ago. We are, quite literally, made of stardust. The remnants of ancient supernovae scattered across space and eventually recycled into new stars, planets, and life. There are different types of supernovae depending on what kind of star explodes and how the explosion happens. The classification system is a bit complicated based on which spectral lines appear in the supernova's light. Type I supernovae don't show hydrogen lines. Type II supernovae do show hydrogen. Within Type I, there are further subdivisions. Type Ia shows silicon. Type Ib and Ik don't. One particular type, called Type Ia supernovae, is especially interesting to astronomers because these explosions are remarkably consistent. They always have about the same brightness at their peak. This makes them perfect standard candles for measuring cosmic distances. Type Ia supernovae occur in binary star systems where one star is a white dwarf, the dense remnant of a dead star. The white dwarf pulls matter from its companion star, gradually gaining mass. When the white dwarf reaches a critical mass, about 1.4 times the mass of the Sun, something called the Chandrasekhar limit, it can no longer support itself. The entire star detonates in a thermonuclear explosion, destroying itself completely. Because Type Ia supernovae always explode at the same mass, they always release roughly the same amount of energy. This means they all have about the same intrinsic brightness. When you see a Type Ia supernova explode, you know how bright it actually is. If it appears dim, it must be far away. If it appears bright, it must be relatively close. By measuring how bright it appears and comparing that to how bright you know it actually is, you can calculate its distance. Here's how it works. If you know how bright something actually is, its intrinsic luminosity, and you can measure how bright it appears from Earth, you can calculate how far away it must be. It's the same principle as estimating distance to a light at night. If you see a light and you know it's a 100-watt bulb, you can tell approximately how far away it is by how dim it appears. The dimmer it looks, the farther away it must be. Light spreads out as it travels through space. Imagine a light bulb at the center of a sphere. The light it emits spreads out evenly in all directions, covering the inside surface of the sphere. Now, imagine a larger sphere. The same amount of light has to cover a bigger area, so the light, at any given point, is dimmer. The area of a sphere grows with the square of its radius, so if you double the distance, the light is spread over 4 times the area, making it 4 times dimmer. Triple the distance, and the light is 9 times dimmer. This is called the inverse square law, and it's fundamental to measuring cosmic distances. Type Ia supernovae are like cosmic light bulbs, where we know the wattage. When we see one explode in a distant galaxy, we can measure its apparent brightness and calculate the galaxy's distance. This is more reliable than other distance measurement methods, which is why astronomers were so excited to use Type Ia supernovae to map the universe's expansion history. In the 1990s, 2 competing research teams set out to use Type Ia supernovae to measure how much the universe's expansion was slowing down. Remember, everyone expected gravity to be slowing the expansion. The question was how much. These measurements would determine whether we were headed for a big crunch or eternal expansion. Both teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, used large telescopes to find and study distant supernovae. They looked at explosions that happened billions of years ago, so far away that their light was just reaching Earth now. By comparing these ancient explosions to more recent ones, they could measure how the expansion rate had changed over cosmic history. The results were shocking. The distant supernovae were dimmer than expected. Not by a lot, but by a consistent, measurable amount. They appeared about 25% farther away than they should have been if the expansion was slowing down as predicted. This could only mean one thing. The expansion wasn't slowing down, it was speeding up. The universe's expansion rate was accelerating, getting faster with time. This was completely unexpected. Gravity, the only force anyone knew about that acted on cosmic scales, should be slowing things down, not speeding them up. It would be like throwing a ball upward and watching it accelerate away from you instead of slowing down and falling back. Something was pushing the universe apart, overcoming gravity's attractive pull. The two teams announced their findings in 1998. The results were checked, rechecked, and verified. More supernovae were observed. Different teams used different methods. Everyone got the same answer. The expansion was accelerating. The three leaders of the two teams, Perlmutter, Schmidt, and Rees, won the Nobel Prize in Physics in 2011 for this discovery. But what was causing the acceleration? What force could push the entire universe apart, overcoming the gravitational attraction of all the matter it contains? Physicists scrambled for explanations, and they found one in an unlikely place, in Einstein's discarded cosmological constant. Here's why it works. As the universe expands, normal matter's density decreases. The same atoms spread over larger volumes mean weaker gravity, but the cosmological constant behaves differently. As a property of space itself, more space means more total energy, while density remains constant. Early in cosmic history, matter was dense and gravity dominated. The constant existed, but couldn't compete. But as expansion diluted the matter, gravity weakened. Eventually, about 5 billion years ago, the constant's influence became strong enough to take over. From that point forward, expansion began accelerating. This vacuum energy is now called dark energy. We label it dark because we can't observe it directly, only through its gravitational effects on the universe's expansion. And it comprises about 68% of all cosmic energy. Normal matter, everything made of atoms, accounts for only 5%. Another 27% is dark matter, invisible substance we detect through gravitational influence but haven't yet identified. Dark energy dominates the cosmos. Einstein added the cosmological constant to create a static universe. He thought he was making a mistake when he included it, and a bigger mistake by not trusting his original equations. But those equations, with the cosmological constant included, turn out to describe the actual universe we live in. The constant is real. The vacuum energy is real. Einstein's biggest blunder was actually a profound insight into the nature of reality. Think about how remarkable this is. Einstein, working with nothing but mathematics and physical intuition, predicted the existence of dark energy 80 years before it was discovered. He got the reasoning wrong. He thought this energy would keep the universe static, when in fact it makes it accelerate. But the fundamental insight that space itself possesses energy. that there's something pushing the universe apart that turned out to be correct. This is how science works at its best. You make predictions based on theory. Sometimes those predictions come from deep insight, and sometimes from mistakes. But then you test them against reality. Observations and experiments are the final judge. Einstein's cosmological constant survived because it matched what we actually observe, not because Einstein wanted it to be true. Let's dig deeper into what dark energy actually is, because even though we've given it a name, we still don't really understand it. Dark energy is one of the greatest mysteries in modern physics. We know it exists because we can see its effects. The acceleration of the universe's expansion is real and measurable. But we don't know what dark energy actually is at a fundamental level. The simplest explanation is that it's exactly what Einstein proposed. A cosmological constant, a fixed amount of energy in every cubic meter or cubic yard of space. This energy doesn't change with time or location. It's the same everywhere, always. It's a property of space itself. Like space has an intrinsic tendency to expand. Think of it this way. Every cubic meter of empty space, a volume about the size of a large refrigerator, contains a tiny amount of dark energy. This energy is incredibly small, about 10 to the power of -9 joules per cubic meter. That's 1/1000th of a joule in a cubic meter. A single AAA battery contains about 5,000 joules of energy, so the dark energy in a cubic meter of space is about 5 trillion times less than the energy in a battery. But space is vast. There's a lot of cubic meters in the universe. When you add up all that tiny energy over all of space, it becomes the dominant form of energy in the cosmos. It's like having an enormous pile of pennies. Each penny is nearly worthless, but billions of pennies add up to real money. But where does this energy come from? One possibility comes from quantum mechanics. In quantum theory, even empty space isn't truly empty. The vacuum is filled with virtual particles constantly popping into existence and then annihilating each other in tiny fractions of a second. These quantum fluctuations should create a kind of vacuum energy, a background energy that fills all of space. Quantum mechanics says that you can't have a perfectly empty vacuum with exactly zero energy. The Heisenberg uncertainty principle, one of the fundamental laws of quantum mechanics, says that if you try to pin down the energy of a region of space to exactly zero, you create infinite uncertainty in when that energy exists, which violates the principle. So the vacuum must have some energy, constantly fluctuating around a non-zero average. When physicists try to calculate how much vacuum energy these quantum fluctuations should produce, they get an answer. But it's the wrong answer, spectacularly wrong. The calculated value is about 10 to the power of 120 times larger than the observed value of dark energy. That's 1 followed by 120 zeros. It's one of the worst predictions in the history of physics. A mismatch so enormous, it's hard to even comprehend. To put this in perspective, if the predicted vacuum energy were correct, the universe would be expanding so fast that atoms couldn't hold together. Galaxies would be torn apart. Stars would be ripped apart. Planets would be destroyed. Life would be impossible. The fact that we exist at all tells us that the actual vacuum energy must be much, much smaller than the naive quantum mechanical prediction. This is called the cosmological constant problem. Why is the observed vacuum energy so much smaller than the predicted value? Why isn't it zero? And why is it the specific value it is, which is just large enough to start dominating the universe's expansion a few billion years ago, coincidentally, right around the time complex life was developing on Earth. Some physicists think there must be some unknown mechanism that cancels out most of the quantum vacuum energy, leaving behind just the tiny amount we observe as dark energy. But we don't know what that mechanism is or why it would leave behind exactly the amount it does. It's like having a complicated calculation that should give you an enormous number, but through some mysterious process involving billions of cancellations, you end up with a tiny number. We don't understand the cancellation mechanism. Others propose that dark energy isn't constant at all. Maybe it changes with time, growing stronger or weaker as the universe evolves. This would be a different kind of energy, not Einstein's cosmological constant, and physicists call it quintessence, after the fifth element of ancient philosophy. If dark energy is quintessence, it could behave differently in the future than it does now, leading to different fates for the universe. Still others suggest we might need to modify general relativity itself. Maybe Einstein's equations work perfectly on the scale of the solar system, but need correction when applied to the entire universe. Maybe there's an additional term or modification that would explain the acceleration without needing dark energy at all. There's even more exotic proposals. Some physicists suggest that dark energy might be connected to extra dimensions of space beyond the three we experience. String theory, a leading candidate for a theory of quantum gravity, predicts that space has 10 or 11 dimensions, most of them curled up so small we can't detect them. Maybe dark energy leaks into our three dimensions from these extra dimensions. Maybe the behavior of gravity changes on cosmic scales because it's affected by these hidden dimensions. Other proposals suggest that our universe might be embedded in a larger structure, a multiverse containing many universes. Maybe dark energy represents the influence of other universes on ours, a kind of pressure from outside pushing our universe to expand. This sounds like science fiction, but it's based on serious mathematical models explored by leading physicists. These are all active areas of research. Physicists are designing new experiments and observations to try to distinguish between these possibilities. They're measuring the universe's expansion rate more precisely, looking for any signs that dark energy is changing with time, and testing general relativity on larger and larger scales. The fate of the universe depends on dark energy's nature. If it's truly a cosmological constant that never changes, then the universe will continue accelerating forever. Galaxies will move apart faster and faster. Eventually, in hundreds of billions of years, galaxies outside our local group will be receding so fast that their light can never reach us. The universe will become dark and cold and empty from any observer's perspective. If dark energy is quintessence that can change strength, then the future is less certain. Maybe it will weaken eventually, and the universe will coast along at a steady expansion rate. Maybe it will strengthen dramatically, tearing apart galaxies, then stars, then planets, then atoms themselves in a big rip. Or maybe it will reverse, becoming attractive instead of repulsive, and the universe will collapse in a big crunch. After all, we simply don't know yet. The observations we have so far are consistent with dark energy being a cosmological constant, unchanging with time. But the error bars are still large enough that we can't rule out other possibilities. Future observations will narrow down the possibilities and hopefully give us a clearer picture of what dark energy really is and what it means for the universe's future. Let's talk about some of the other interpretations and implications of Einstein's so-called blunder, because the story of the cosmological constant is really a story about how science works and how even mistakes can lead to progress. First, was this really Einstein's biggest mistake? Einstein himself apparently thought so, or at least that's what he told people later in life. But historians of science have pointed out that Einstein made other errors that were arguably more significant. For example, Einstein spent the last 30 years of his life trying to develop a unified field theory, a single framework that would combine gravity and electromagnetism. He was trying to find a theory of everything, a set of equations that would describe all the forces of nature and all the particles of matter. He pursued this goal obsessively, filling notebooks with calculations and trying approach after approach. He never succeeded. And in hindsight, his approach was doomed from the start because he was trying to unify the wrong things. He was ignoring quantum mechanics, which he deeply mistrusted, and focusing only on classical fields. But the universe is quantum at its core. Any theory of everything must incorporate quantum mechanics. Einstein's refusal to fully embrace quantum theory, despite being one of its founders with his work on the photoelectric effect, meant he was looking in the wrong direction. Those 30 years could have been spent on more productive research. Einstein could have contributed to quantum field theory or nuclear physics or other areas where his insights might have been valuable. Instead, he pursued a dead end, isolated from mainstream physics, increasingly seen as out of touch by younger physicists. From that perspective, his quest for a classical, unified field theory was a bigger mistake than adding the cosmological constant. But there's a difference. The unified field theory work was simply wrong. It led nowhere and contributed nothing to future physics. The cosmological constant, on the other hand, turned out to describe something real about the universe, even if Einstein added it for wrong reasons. So while the unified field theory work might have been a bigger waste of Einstein's time and talent, the cosmological constant story is more interesting because of its resurrection in modern cosmology. It's also worth noting that the cosmological constant might not have been a mistake at all in the context of its time. In 1917, there was no evidence the universe was expanding. Einstein was working from the best available information, which suggested a static cosmos. Adding a term to his equations to allow a static solution was perfectly reasonable, given what was known then. The mistake, if there was one, was not removing the constant as soon as better observations became available. But even that's understandable. Scientific paradigms don't shift instantly when new data arrives. It takes time for evidence to accumulate, for alternative explanations to be ruled out, and for consensus to form. Einstein accepted Hubble's observations fairly quickly by the standards of scientific revolutions. Another interesting aspect of this story is what it tells us about the relationship between mathematics and physics. Einstein's equations predicted an unstable universe. He modified them to get a static universe. The original equations turned out to be right, but the modified version also turned out to describe something real. This raises a philosophical question. Do mathematical equations describe reality, or do they just provide useful models that approximately match observations? Physicists generally lean toward the first view. They believe the universe operates according to mathematical laws, and our equations, when correct, are discovering those laws rather than just modeling observations. But the cosmological constant story complicates this. Einstein added a term for non-physical reasons to get an answer he wanted. By pure mathematics, the term was allowed but not required. And yet it turned out to be necessary to describe the actual universe. Does this mean the mathematics somehow knew more than Einstein did? Or is it just a lucky coincidence? There's no clear answer. But it does suggest that mathematics has a way of surprising us, of containing truths we don't immediately recognize. Einstein's equations, in their full generality, including all the terms that are mathematically possible, described a universe that could be static with fine-tuned lambda, or expanding, or contracting, or accelerating. The equations contained all these possibilities. Observations told us which possibility is real. Let's also consider what this means for scientific reasoning and how scientists should approach their work. Einstein let his philosophical preferences guide his modifications to general relativity. He wanted an eternal, unchanging universe, and he adjusted his equations to provide one. In the end, this was wrong. The universe isn't static. Does this mean scientists should never let philosophical or aesthetic considerations guide their work? Should they only follow the math wherever it leads? Not necessarily. Physical intuition, aesthetic judgment, and philosophical reasoning have played crucial roles in many scientific advances. Einstein himself relied heavily on thought experiments and intuitive reasoning to develop both special and general relativity. The lesson isn't that philosophical reasoning is bad. It's that observations are the ultimate arbiter. You can use whatever reasoning you want to develop theories and make predictions. But then you have to test those predictions against reality. And when reality disagrees with your preferences, you have to change your mind. Einstein did change his mind when Hubble's observations came in. He accepted that the universe was expanding and that his static model was wrong. That's good science. Where he perhaps erred was in adding the cosmological constant in the first place without observational justification, purely to get a desired result. The modern attitude in physics is generally more conservative about adding new terms or modifying successful theories. If your equations predict something that seems strange or counterintuitive, you should think very carefully before changing them. Often, the strange prediction turns out to be correct. Special relativity predicted time dilation, which seemed absurd when Einstein first proposed it. General relativity predicted black holes, which many physicists thought must be mathematical artifacts rather than real objects. Quantum mechanics predicted particles could be in multiple places at once, which violated common sense. All of these strange predictions turned out to be correct. So when your beautiful, successful theory predicts something you don't like, maybe the problem is with your intuition, not with the theory. Maybe the universe is stranger than you thought. That's the lesson of the cosmological constant. Einstein's intuition told him the universe should be static. His equations told him it couldn't be. He modified the equations. The equations were right. Let's zoom out and look at the bigger picture of what we've learned about the universe, thanks to Einstein's work, both his successes and his mistakes. General relativity has become the foundation of modern cosmology. Every major discovery about the large-scale structure and evolution of the universe has been interpreted through the framework Einstein provided. We've learned that space and time are not separate, absolute things, but are woven together into a single fabric called spacetime. This fabric can bend, stretch, compress, and ripple. Massive objects create depressions in spacetime, and we experience these depressions as gravity. We've learned that the universe had a beginning, the Big Bang, about 13.8 billion years ago. Before that moment, there was no space, no time, no matter, no energy. The Big Bang wasn't an explosion in space. It was the beginning of space itself, the moment when space-time came into existence and began expanding. We've learned that this expansion is accelerating, driven by dark energy that makes up most of the universe's total energy content. We don't fully understand what dark energy is, but we can measure its effects and predict its influence on the universe's future. We've learned that most of the matter in the universe is dark matter, another form of invisible substance that doesn't interact with light but creates gravitational effects. Galaxies are embedded in huge halos of dark matter that outweigh the visible matter by a factor of 6 to 1. Without dark matter's extra gravity, galaxies would fly apart. Stars would not orbit the way they do. We've learned about black holes, regions where space-time is curved so severely that not even light can escape. We've observed stellar mass black holes created by collapsing stars, supermassive black holes millions or billions of times the sun's mass sitting at the centers of galaxies, and even the merger of two black holes detected through gravitational waves. We've learned about the cosmic microwave background, the afterglow of the Big Bang, a faint radiation that fills all of space and provides a snapshot of what the universe looked like when it was only 380,000 years old. By studying tiny variations in this radiation, we can learn about the seeds that grew into galaxies and the fundamental properties of the cosmos. All of this understanding rests on the foundation Einstein built with general relativity. His equations have been tested countless times in countless ways, from the bending of starlight during eclipses, to the time dilation of GPS satellites, to the gravitational waves from colliding black holes. Every test has confirmed that Einstein was right. And yet, general relativity is not the final word. We know it must be incomplete because it doesn't play nicely with quantum mechanics. General relativity is a classical theory. It describes spacetime as smooth and continuous. Quantum mechanics says everything is discrete and probabilistic at the smallest scales. These two frameworks, our best theories of the very large and the very small, contradict each other when pushed to extremes. Inside a black hole, at the singularity where all the mass is compressed to infinite density, both gravity and quantum effects become important. General relativity predicts infinite density and infinite space-time curvature. But quantum mechanics doesn't allow true infinities. Something has to give. At the moment of the Big Bang, the entire universe was compressed to a size smaller than an atom. Again, both gravity and quantum effects matter. We can't use general relativity alone to describe what happened at that moment because we need quantum gravity, a theory that combines general relativity with quantum mechanics in a consistent way. Physicists have been working on quantum gravity for decades. String theory, loop quantum gravity, and other approaches try to build a framework where space-time itself becomes quantum, where space and time are made of discrete units rather than being continuous. But we don't have a complete, tested theory yet. This is one of the great unsolved problems in physics. When we do finally develop a theory of quantum gravity, it might change our understanding of dark energy and the cosmological constant. The vacuum energy that makes up dark energy is inherently quantum in nature. A complete theory should be able to calculate its value from first principles, explaining why it is what it is, rather than just measuring it. That calculation might resolve the cosmological constant problem, or might reveal that dark energy is something entirely different from what we currently think. So Einstein's legacy in cosmology is twofold. He gave us the framework we still use to understand the universe, and he left us with puzzles that still haven't been solved. The cosmological constant was his attempt to solve one puzzle, his desire for a static universe. He removed it when observations showed that wasn't the right puzzle to solve. Modern cosmology brought it back to solve a different puzzle, the acceleration of cosmic expansion. But the deeper puzzle of why dark energy has the value it does remains unsolved. Let's talk about what all this means for the future, both the future of cosmology as a science and the future of the universe itself. Where do we go from here? For cosmology, the immediate goal is to better understand dark energy. Is it truly constant, or does it change with time? Is it the vacuum energy predicted by quantum mechanics, or something else entirely? To answer these questions, astronomers are conducting increasingly precise observations of the universe's expansion history. Projects like the Darkenergy Survey and the upcoming Vera-Rubin Observatory are mapping millions of galaxies, measuring their distances and redshifts to trace how the expansion rate has changed over time. The James Webb Space Telescope is looking at some of the most distant galaxies in the universe, seeing them as they were more than 13 billion years ago when the universe was young. By comparing the expansion rate at different times in cosmic history, astronomers can determine whether dark energy has been getting stronger, weaker, or staying the same. Current data suggests it's constant, but the uncertainties are still large. Another decade of observations should narrow down the possibilities considerably. There are also efforts to directly detect dark energy particles, if such particles exist. Some theories propose that dark energy might be carried by a new type of particle, similar to how electromagnetic force is carried by photons. Experiments in underground laboratories are searching for these hypothetical particles, though most physicists think they probably won't find anything because dark energy doesn't seem to interact with normal matter, except through gravity. The most exciting possibility would be finding evidence that general relativity needs to be modified on cosmic scales. If observations showed that gravity behaves differently in different parts of the universe or at different times, that would be revolutionary. It would mean Einstein's theory, while correct in our solar system and our galaxy, breaks down when applied to the universe as a whole. That would open up entirely new areas of physics to explore. As for the universe's future, if dark energy is truly a cosmological constant that never changes, the story is rather bleak, at least from a human perspective. The universe will continue expanding forever. Galaxies outside our local group are already receding from us, and that recession is accelerating. Eventually, in about 100 billion years, all galaxies beyond our immediate neighborhood will have receded beyond our cosmic horizon. Their light will be stretched to such long wavelengths by the expansion of space that we'll never see them again. Think about what this means. An astronomer living in the distant future, 100 billion years from now, looking out into the universe with the most powerful telescopes imaginable, will see something completely different from what we see today. They'll see only our local group of galaxies, the Milky Way, and perhaps a few dozen nearby galaxies that have merged with us or remain gravitationally bound to us. Beyond that, nothing, just empty darkness, extending in all directions forever. To an astronomer living 100 billion years from now in the Milky Way, or in one of the few nearby galaxies that will have merged with us by then, the observable universe will appear to contain only our local group of galaxies surrounded by empty space. They'll see no evidence of cosmic expansion because everything observable will be gravitationally bound together. They'll have no way to know that there are trillions of other galaxies beyond their horizon. They won't be able to see the cosmic microwave background radiation because it will have been redshifted into invisibility. They won't be able to see distant galaxies moving away. They won't be able to detect any of the evidence that we currently use to understand the Big Bang and the universe's history. From their perspective, the universe will appear to consist of a single large galaxy surrounded by infinite empty space. They might not even be able to figure out that the universe had a beginning. In fact, they might not even know that the Big Bang happened. The cosmic microwave background radiation will have been redshifted to such long wavelengths that it will be undetectable. The evidence that our current generation of astronomers has used to understand the universe's history and structure will simply be gone. carried beyond the horizon by the accelerating expansion. This is a sobering thought. We live at a privileged time in cosmic history when the universe's nature and history are observable. Past a certain point in the future, that window closes. The universe becomes opaque to its own history. Information about where we came from and what else exists out there becomes permanently inaccessible. Future civilizations, if any exist, will be unable to learn what we know about the cosmos simply because the evidence will have moved beyond their reach. On even longer timescales, the universe becomes truly lonely. Stars will continue forming from available gas for a few tens of billions of years. Eventually, star formation will stop when all the available gas has been converted to stars or locked up in black holes and dead stellar remnants. The last stars will burn out in about 10 trillion years or so. That's 10,000 billion years, about 700 times longer than the current age of the universe. After that, the universe will be dark. Dead stars, brown dwarfs, white dwarfs, neutron stars, and black holes will be all that remains. Even these will eventually fade. White dwarfs will cool to black dwarfs, dark cinders of carbon and oxygen floating through space. Neutron stars will cool, though this takes an incredibly long time because they're so dense and have so little surface area to radiate away their heat. And black holes will evaporate through Hawking radiation, though this process takes an incomprehensibly long time. Stephen Hawking predicted in the 1970s that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation is incredibly faint and incredibly slow, but given enough time, it will cause even the largest black holes to evaporate completely. A solar mass black hole evaporates in about 10 to the power of 67 years. That's 1 followed by 67 zeros. To put this in perspective, the universe is currently only about 10 to the power of 10 years old, 14 billion years. A solar mass black hole lasts about 10,000 trillion times longer than the current age of the universe. A supermassive black hole like the one at the center of our galaxy takes even longer, around 10 to the power of 100 years. These numbers are so large they become meaningless. We're talking about timescales that are to the age of the universe as the age of the universe is to a single second. By the time all black holes have evaporated, the universe will be unimaginably old and unimaginably empty. Eventually, even protons might decay, though this is speculative. Some theories of particle physics predict that protons are unstable with a lifetime of 10 to the power of 40 years or so. We've never observed proton decay, so if it happens, it must be incredibly rare. But given enough time, if protons do decay, then eventually all normal matter will dissolve into radiation. The universe will contain nothing but a thin mist of photons and other fundamental particles, growing more dilute as space continues expanding forever. This is called the heat death of the universe, a state of maximum entropy where no energy differences exist, no work can be done, and nothing interesting ever happens. The universe doesn't end with a bang. It fades into an eternal, unchanging darkness. All the stars, all the galaxies, all the black holes, all the structure we see today will have dissolved into a uniform sea of particles, spreading ever farther apart through an eternally expanding space. In this far future, in this heat-death scenario, the universe approaches a state where nothing changes anymore. There are no temperature differences to drive heat flows. There's no available energy to do work. Entropy, the measure of disorder, has been maximized. Everything that could happen has happened. Time itself becomes meaningless because nothing changes from one moment to the next. That's if dark energy is constant. If it's quintessence that grows stronger with time, the ending could be more dramatic. If dark energy's repulsive force keeps growing, it will eventually overcome not just cosmic expansion, but also the forces holding galaxies together, then solar systems, then planets, then atoms. In this Big Rip scenario, the universe's expansion accelerates so rapidly that everything gets torn apart. First, galaxy clusters unbind. The galaxies that are currently held together by their mutual gravity drift apart as dark energy overcomes that gravity. Then individual galaxies unbind and their stars scatter. Our Milky Way, which has held together for over 13 billion years, would fly apart, its hundreds of billions of stars flung in all directions. Then solar systems come apart as planets are ripped away from their stars. The Earth would be torn from its orbit around the Sun and flung into the cold darkness of space. Then planets themselves are pulled apart by tidal forces. The Earth would be stretched and torn, first breaking into large fragments, then smaller pieces, then individual rocks, then molecules, then atoms. Eventually, even atoms are ripped apart, electrons torn away from nuclei. The electromagnetic force that holds atoms together would be overcome by the acceleration of space itself. Matter as we know it would cease to exist, reduced to a plasma of individual particles. Finally, even atomic nuclei might be torn apart. Protons and neutrons split into their constituent quarks. The universe ends in a cataclysm where space expands so fast that nothing can hold together anymore. The Big Rip is more dramatic than the heat death, but it's also quicker. Instead of the slow fade over Google years that heat death entails, the Big Rip happens relatively quickly once the acceleration becomes strong enough. Current estimates, if the Big Rip is real, suggest it would occur perhaps 20 to 50 billion years from now. Still a long time by human standards, but nothing compared to the timescales of heat death. Most physicists think the Big Rip is unlikely. Current observations suggest dark energy is probably constant or nearly constant, but we can't entirely rule it out yet. The fate of the universe remains uncertain. There's also a fourth possibility worth mentioning, though it's quite speculative. Some theories suggest that the vacuum state of the universe might not be stable. We might be living in a false vacuum, a local minimum of energy that appears stable but isn't truly the lowest possible energy state. If that's true, then at some random point in the future, a quantum fluctuation could trigger a transition to the true vacuum state. This would create a bubble of true vacuum that expands at the speed of light, converting the false vacuum to the true vacuum wherever it passes. Inside the bubble, the laws of physics might be different. Particles might have different masses. Forces might have different strengths. Atoms as we know them might not be able to exist. This bubble would destroy everything it touches, rewriting the rules of physics as it expands. There would be no warning because it expands at light speed. You wouldn't see it coming. One moment you exist, the next moment you don't. Converted into whatever configurations of matter and energy are stable in the true vacuum. This sounds like science fiction, but it's a real possibility allowed by quantum field theory. We have no way of knowing whether our vacuum is truly stable or just metastable, appearing stable but not actually being in the lowest energy state. If it's metastable, the universe could end at any moment, though the probability of this happening in any given year is astronomically small. Most physicists don't lose sleep over vacuum decay because there's nothing we can do about it and no evidence that it's actually a threat. It's more of a theoretical curiosity than a practical concern. But it does illustrate how much we still don't know about the universe's fundamental nature. Let's circle back to Einstein himself and what his story teaches us about science and creativity. Einstein was a revolutionary thinker who changed our understanding of reality more profoundly than perhaps any other single individual in history. His work on special relativity, general relativity, and quantum mechanics provided the foundations for modern physics. But he was also human, prone to mistakes, biases, and errors of judgment. He added the cosmological constant because he preferred a static universe for philosophical reasons. He spent decades pursuing a unified field theory that led nowhere because he refused to fully embrace quantum mechanics. He made errors and wrong turns just like any other scientist. Einstein's relationship with quantum mechanics is particularly interesting and tragic. He was one of the founders of quantum theory, winning the Nobel Prize for his explanation of the photoelectric effect, which showed that light behaves as particles in certain situations. But as quantum mechanics developed through the 1920s, taking on its modern form with wave functions, probability, and uncertainty, Einstein became increasingly uncomfortable with where the theory was heading. He famously declared that God does not play dice with the universe, expressing his discomfort with the probabilistic nature of quantum mechanics. In the classical physics he grew up with, everything was deterministic. If you knew the exact state of a system at one moment, you could in principle calculate its state at any future moment. Quantum mechanics said no. The best you can do is calculate probabilities. The universe is fundamentally uncertain at its core. Einstein thought this couldn't be the final word. He believed quantum mechanics must be incomplete, that there must be deeper variables, hidden mechanisms that would restore determinism and certainty if only we could discover them. He spent enormous effort trying to prove quantum mechanics was incomplete or contradictory, devising thought experiments meant to expose its problems. The most famous of these was the EPR paradox, named after Einstein, Podolsky, and Rosen, who published it in 1935. The thought experiment showed that quantum mechanics seemed to allow instantaneous influences between distant particles, what Einstein mockingly called spooky action at a distance. He thought, this proved quantum mechanics must be wrong or incomplete. But experiments later showed that Einstein was wrong. The spooky action at a distance is real. Quantum entanglement, as it's now called, has been demonstrated countless times. It's not just theoretical. It's been measured, tested, and even used in practical applications like quantum cryptography and quantum computing. Einstein's intuition that it couldn't be real turned out to be mistaken. The universe really is that strange. So Einstein spent the last 30 years of his life pursuing a unified field theory, trying to merge gravity and electromagnetism into a single framework while ignoring quantum mechanics. Meanwhile, the physics community moved on without him. Younger physicists developed quantum field theory, figured out the weak and strong nuclear forces, discovered new particles, and built the standard model of particle physics. All of this passed Einstein by because he was working in isolation on a problem that couldn't be solved with the tools he was using. What made Einstein special wasn't that he was always right. It was his willingness to think differently, to question assumptions that everyone else took for granted, and to follow his mathematical and physical intuition even when it led to bizarre conclusions. He imagined riding alongside light beams as a teenager. He wondered what would happen if space and time weren't absolute. He asked what gravity would look like if it wasn't a force, but a curvature of space-time. These thought experiments, these acts of imagination, these willingness to question everything, that's what led to his greatest discoveries. And those same qualities led to his mistakes. He questioned whether the universe had to be dynamic. He imagined it could be static and eternal. He followed that intuition and added a term to make his equations match his vision. The lesson is that mistakes are part of the process. You can't be at the cutting edge of knowledge without sometimes being wrong. The key is to let observations and experiments guide you, to be willing to change your mind when the evidence doesn't match your expectations, and to keep pushing forward even when you make errors. Einstein did all of this. He made mistakes, but he corrected them when better information became available. He pursued dead ends, but he never stopped thinking about fundamental questions. And some of his mistakes, like the cosmological constant, turned out to contain deep truths that he couldn't have anticipated. Science is fundamentally a collective enterprise. Even though we often focus on individual genius, Einstein built on the work of Maxwell, Lorentz, Poincaré, and others who had been struggling with the same problems he solved. Hubble built on Leavitt's work on Cepheid variables. The supernova teams that discovered dark energy built on decades of work by astronomers measuring distances and mapping galaxies. Every discovery stands on the shoulders of what came before. But science also needs individuals willing to take big risks, to propose radical ideas, to question the foundations of what everyone thinks they know. Einstein was exceptional at this. He had the mathematical skill to work out the details of his ideas, but more importantly, he had the physical intuition to know which questions to ask and the courage to follow wherever those questions led. This is the nature of science. It's messy, uncertain, full of wrong turns and dead ends, but it's also self-correcting. Bad ideas get weeded out by observation and experiment. Good ideas survive and become stronger as more evidence accumulates. And sometimes ideas that seemed bad turn out to be good after all, when viewed from a different perspective. The cosmological constant story is a perfect example of this process. Einstein added it for wrong reasons. It was removed as unnecessary. It was brought back when new observations demanded it. Now it's a central part of cosmology, describing the dominant component of the universe's energy content. The story has come full circle, but in an unexpected way that nobody could have predicted. What does this tell us about the nature of physical law and our ability to understand the universe? On one level, it's humbling. Even Einstein, working at the peak of his powers, couldn't foresee all the implications of his equations. He added and removed the cosmological constant based on incomplete information and philosophical preferences. He missed the opportunity to predict the universe's expansion, but on another level, it's empowering. The fact that the equations contained the right answer all along, that the mathematics knew more than Einstein did, suggests that there really are underlying laws of nature waiting to be discovered. The universe operates according to mathematical principles. Our equations, when we get them right, are discovering these principles rather than just inventing convenient fictions. General relativity has now been tested for over a century. It's passed every test. It's made predictions that seemed absurd at the time, but turned out to be correct. Black holes exist. Gravitational waves exist. Time runs at different rates in different gravitational fields. Light bends around massive objects. The universe is expanding, and that expansion is accelerating. All of this follows from Einstein's equations. That doesn't mean general relativity is the final word. We know it must be incomplete because it doesn't include quantum mechanics. We know there are puzzles it can't solve, like what happens at the center of a black hole, or what happened at the moment of the Big Bang. But within its domain of applicability, general relativity works. It describes reality. The mathematics maps onto the physical world in a deep and precise way. This is one of the great mysteries of physics and mathematics. Why does mathematics work so well to describe nature? Why do equations written on paper correspond so precisely to measurements made with instruments? There's no obvious reason why the universe should be mathematical, but it is. Galaxies orbit according to mathematical laws. Light follows mathematical paths. Particles interact according to mathematical rules. Everything we've studied follows mathematical patterns. Eugene Wigner, a physicist who won the Nobel Prize for his work on quantum mechanics, wrote a famous essay called "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He marveled at how mathematical concepts developed for purely abstract reasons often turn out to be exactly what's needed to describe physical phenomena. Complex numbers, group theory, differential geometry, all of these mathematical tools were invented by mathematicians following their own aesthetic sense of what was interesting or elegant. Later, physicists found these tools were exactly what they needed to describe quantum mechanics, particle physics, and relativity. Why should this be the case? Why should the pure mathematics created by human minds match the structure of external reality? It's a deep question without a clear answer. Maybe our minds are somehow tuned by evolution to think mathematically because that reflects how the universe actually works. Maybe there's something fundamental about mathematical structure that physics must follow. Or maybe we're selecting the mathematical frameworks that work and ignoring the countless ones that don't, creating an illusion of unreasonable effectiveness. Whatever the answer, the fact remains that mathematics is our most powerful tool for understanding the cosmos. Einstein's equations are mathematical. The cosmological constant is a mathematical term. Dark energy is observed through measurements that are then fit to mathematical models. All of our understanding of the universe flows through this mathematical language. Let's talk about one more aspect of this story that's worth reflecting on: the role of technology in driving scientific discovery. Hubble's observations that revealed the expanding universe were only possible because of the 100-inch telescope at Mount Wilson, which was the largest and most powerful telescope in the world at the time. Without that technology, without the ability to see faint distant galaxies and measure their spectra precisely, Hubble couldn't have made his discovery. Similarly, the supernova observations that revealed dark energy required large telescopes, sensitive digital cameras, and powerful computers to process the data. The detection of gravitational waves required the LIGO experiment, a marvel of engineering that can measure distances changing by less than the width of a proton across arms 4 kilometers or 2.5 miles long. The cosmic microwave background was mapped by satellites like COBE, WMAP, and Planck that measured temperature variations of a few millionths of a degree across the sky. Every major advance in cosmology has been enabled by technological progress. Better telescopes let us see farther and more clearly. Better detectors let us measure fainter signals. Better computers let us analyze more data and run more sophisticated simulations. The discoveries don't come from technology alone. You need ideas, theories, questions to guide what you're looking for. But the technology is what lets you actually look. This creates an interesting dynamic. Theorists like Einstein develop mathematical frameworks that make predictions. Observers and experimentalists build the instruments to test those predictions. When observations confirm theory, both are strengthened. When observations contradict theory, both have to adapt. Theory guides what to look for, but observations determine what's actually true. The cosmological constant sat in Einstein's equations for decades before technology advanced enough to detect its effects. The supernova observations of the 1990s required digital cameras that didn't exist in Einstein's time. If he'd lived to see these observations, he would have learned that his blunder was actually correct, that the constant he added and removed really did describe something fundamental about the universe. This back and forth between theory and observation, between mathematics and measurement, between prediction and confirmation, is the engine that drives physics forward. Neither theory nor observation alone is sufficient. You need both. Working together, challenging each other, refining understanding through iteration. As we look to the future, the next generation of telescopes and experiments will test our current understanding even more rigorously. The Vera Rubin Observatory will survey the entire visible sky every few nights, discovering millions of new objects and tracking how they change with time. The James Webb Space Telescope is already finding the most distant galaxies in the universe, seeing them as they were in the first few 100 million years after the Big Bang. The square-kilometer array, when complete, will be the world's largest radio telescope, studying everything from the cosmic microwave background to the formation of the first stars to the distribution of neutral hydrogen throughout the universe. The 30-meter telescope and the extremely large telescope will have mirrors so large they can see Earth-like planets around nearby stars and study the atmospheres of those planets for signs of life. Each of these instruments will test our understanding of cosmology, dark energy, and general relativity in new ways. They might confirm that dark energy is truly a cosmological constant. They might reveal that it changes with time. They might find evidence that general relativity breaks down on the largest scales. Or they might discover something entirely unexpected, something nobody has even imagined yet. That's the exciting part about science. You build your best theories based on current knowledge. You make predictions, you test them. And sometimes the universe surprises you. Sometimes you find something you weren't looking for, something that doesn't fit any existing framework, something that forces you to rethink everything. Dark energy was one of those surprises. Nobody expected the universe's expansion to be accelerating. The supernova teams were trying to measure how much the expansion was slowing down, not whether it was speeding up. The discovery was a complete shock, forcing cosmologists to revise their understanding of the universe's composition and fate. There will be more surprises. We don't know what they'll be or when they'll come. But history shows that every time we look at the universe in a new way, with new instruments or new techniques, we find something unexpected. The universe is more strange, more beautiful, and more surprising than we imagine. Einstein's cosmological constant teaches us to stay humble. Even the greatest minds can miss things or get things wrong. But it also teaches us to stay curious. The universe has secrets waiting to be discovered. Mathematics gives us a language to describe those secrets. Observations test whether our descriptions are correct, and technology gives us new eyes to see what was previously hidden. In the end, Einstein's biggest mistake wasn't really a mistake at all. It was a step in the long process of understanding the cosmos. He added a term to his equations for wrong reasons, but the term turned out to be necessary for right reasons. He removed it when he thought it was wrong, but it came back when observations demanded it. The story has ambiguity, uncertainty, and surprise, just like science itself. As we close, let's think about what this means for us. For people living in the early 21st century, trying to understand our place in the cosmos. We live at a remarkable moment in history. For the first time, our species can see almost the entire observable universe. We can look back in time to when the first stars formed. We can map the distribution of galaxies across billions of light years. We can measure the fundamental parameters that determine the universe's composition and fate. We've learned that the universe is larger, older, and stranger than anyone imagined just a century ago. We've learned that most of what exists is invisible to us, dark matter and dark energy, that we detect only through their gravitational effects. We've learned that space itself is dynamic, expanding and carrying galaxies with it. We've learned that time is not absolute, that it runs at different rates depending on motion and gravity. The story of how we learned all this is remarkable in itself. It involved countless scientists working over generations, each contributing a piece to the puzzle. Some, like Einstein and Hubble, made revolutionary discoveries that changed everything. Others made smaller, but still essential contributions, developing techniques, building instruments, making careful observations that constrained theories and tested predictions. The cosmological constant story shows us that science isn't a straight line from ignorance to knowledge. It's a winding path with many side trails, dead ends, and unexpected turns. Einstein added the constant, then removed it. Decades passed. Then observations demanded its return. But now it meant something different, described something different. The journey from Einstein's static universe to our accelerating universe took almost a century and involved thousands of scientists. All of this understanding rests on Einstein's work. General relativity provides the framework we use to interpret our observations and understand the cosmos. The cosmological constant, Einstein's blunder that wasn't really a blunder, describes the dominant form of energy in the universe. Every time you hear about dark energy or the accelerating expansion or the ultimate fate of the cosmos, you're hearing about Einstein's legacy. When Einstein published General Relativity in 1915, he couldn't have imagined where it would lead. He was solving a specific problem: how to incorporate gravity into his theory of spacetime. He wasn't trying to describe the entire universe or predict dark energy or explain the Big Bang. These applications of his theory came later, as other physicists and astronomers built on his foundation. This is typical of great scientific theories. They often turn out to be more powerful and more general than their creators imagined. Newton's laws of motion were developed to explain planetary orbits, but they also describe billiard balls, pendulums, and rocket trajectories. Maxwell's equations of electromagnetism were developed to unify electricity and magnetism. But they also predicted radio waves, which Maxwell himself didn't anticipate. Darwin's theory of evolution by natural selection was developed to explain the diversity of life, but it also provides insights into psychology, sociology, and even computer science through genetic algorithms. Einstein's general relativity has proven remarkably robust and versatile. It describes the orbit of Mercury around the Sun with its tiny deviations from Newton's predictions. It describes the bending of light around massive objects. It describes gravitational waves from colliding black holes billions of light years away. It describes the expansion of the entire universe and predicts its ultimate fate, all from a single, elegant, mathematical framework that Einstein worked out by thinking deeply about the nature of gravity, space, and time. But we're also at the beginning of understanding, not the end. We don't know what dark energy really is. We don't know what dark matter is. We don't know how to reconcile general relativity with quantum mechanics. We don't know what happened at the exact moment of the Big Bang. We don't know if there are other universes beyond our own. We don't know whether the laws of physics could have been different, or why they're the specific laws we observe. These mysteries aren't failures of science. They're the frontier, the edge of current knowledge where the next generation of discoveries will be made. Every answer raises new questions. Every solution reveals new puzzles. That's how science progresses. We solve one mystery only to find three more hiding behind it. Consider what we've learned just in the last few decades. In 1990, we knew of no planets outside our solar system. Now we've confirmed over 5,000 exoplanets, with thousands more candidates waiting. In 1990, gravitational waves were still theoretical predictions. Now we detect them regularly from colliding black holes and neutron stars. In 1990, dark energy was unknown. Now we know it's the dominant component of the universe. What will we learn in the next few decades? What discoveries await that we can't even imagine? The James Webb Space Telescope is already finding galaxies in the early universe that challenge our understanding of galaxy formation. Future telescopes will see even farther and more clearly. New experiments will test fundamental physics in new regimes. We might discover what dark matter actually is. We might detect quantum gravitational effects. We might find life on other worlds. These are the great questions of our time. Future generations will have better answers than we do, just as we have better answers than Einstein did. The process continues. Each generation builds on what came before, correcting mistakes, refining understanding, pushing further into the unknown. Einstein showed us that even mistakes can be productive if you approach them with honesty and willingness to change your mind when evidence demands it. He added the cosmological constant, removed it, and eventually it came back because the universe itself insisted on its reality. The story is messy and human, but it led to profound insights about the nature of reality. His legacy extends beyond specific discoveries or equations. He demonstrated that the universe can be understood through mathematics and reason. Reality is often stranger than we imagine. Common sense can mislead us, and only careful observation and rigorous theory reveal the truth. Intellectual courage is essential for progress. You must be willing to question everything, even the most basic assumptions, to make revolutionary discoveries. Einstein also showed us the limits of individual genius. Even the greatest mind can miss things, make mistakes, let biases cloud judgment. Science needs individual brilliance, but it also needs collective effort, peer review, replication, and the willingness to change course when evidence demands it. No single person, no matter how smart, can see everything or know everything. We need diverse perspectives, different approaches, and many people working on problems from different angles. So the next time you look up at the night sky and think about the universe, remember this story. Remember that the cosmos is stranger than we imagine. Remember that the universe is expanding, accelerating into a future we're only beginning to understand. And remember that the equations describing all of this, the mathematical language that lets us comprehend the incomprehensibly large and complex, were largely given to us by one man thinking deeply about the nature of gravity, space, and time. Einstein's genius wasn't that he never made mistakes. It was that he had the courage to propose revolutionary ideas, the skill to work out their mathematical implications, and the honesty to admit when observations proved him wrong. He changed how we think about space, time, matter, energy, and gravity. He showed us that the universe operates according to elegant mathematical laws that we can discover and understand. The cosmological constant represents both misjudgment and prescient insight. Added to preserve an incorrect model of the cosmos, that same term turned out to describe the dominant energy driving everything we observe. Dark energy determines the universe's accelerating expansion and will shape its ultimate fate. Einstein couldn't have known this in 1917, but his mathematics contained the truth, even when he misunderstood its implications. This teaches us humility. Even the smartest people can be wrong. Even revolutionary theories can contain hidden truths their creators don't understand. Science progresses, not because individual scientists are infallible, but because the scientific method eventually sorts truth from error through observation and experiment. It also teaches us persistence. Einstein labored on general relativity for almost a decade, trying different approaches, learning new mathematics, pushing through obstacles. Discovery rarely comes easily, and it teaches us openness. When Hubble's observations revealed expansion, Einstein accepted it despite his philosophical preferences. He acknowledged error publicly. That willingness to revise understanding in the face of evidence, to abandon cherished ideas when reality disagrees, is essential to science. Thank you for joining me on this journey through cosmology and history. If you found this exploration valuable, a like or subscribe would mean a lot. And remember, in the vast darkness of the cosmos, even the greatest minds stumble. But those stumbles, those errors, those blunders, they're all part of humanity's long struggle to understand where we are, how we got here, and where we're going. The universe is expanding into a future we can barely imagine, and we're going along for the ride, asking questions, making mistakes, and slowly, gradually learning the truth. Good night.